Welcome to the webinar on quantum computing applications in the financial sector, which is jointly organized by the Keene Institute at UNC Chapel Hill and the NC State IBM Q-Hub. I'm your host. My name is Eric Geisels. I'm a professor of economics at UNC Chapel Hill and a professor of finance at the Keene Flagler Business School. This webinar series actually has been running for almost a year. We started out about a year ago with the first presentation by Stefan Werner from IBM Research Zurich, one of the leading scholars in the field. It was followed by a number of webinars by Isaiah Hull from the Swedish Central Bank, Roman Oros from Donostia International Physics Center, Tomoki Tanaka from Keio University and Mitsubishi Financial Group, Daniel Egger from IBM Research, also in Zurich, and Xiaoan Hu from JP Morgan. We're ending the first year with a real treat. I have the privilege of hosting today Seth Lloyd from MIT. Seth Lloyd is one of the pioneers of quantum computing. He has done seminal work in this field, including proposing the first technologically feasible design for a quantum computer. And in recent years, Seth has actually written quite a number of papers on quantum algorithms for standard machine learning algorithms, procedures such as principal components, support vector machine, deep learning, etc. And that's exactly the topic that he's going to be talking about today. He's going to talk about quantum machine learning algorithms for financial analysis. Before we start, just one thing about housekeeping. At the bottom of your screen, there is a Q&A button, so please feel free to write your questions during Seth's presentation. With that being said, welcome Seth, and please share your screen, and we're ready to go.
Okay, good. So I'm going to just say a little bit before I put the talk up. Can people see me?
Yes, I can see you.
Okay, great. Thank you, Eric. It's a great pleasure to be here. I only wish I were there because I love Chapel Hill. It's one of my favorite places, and I'm very sorry I can't be there in person.
You have good taste.
Good taste in barbecue, if nothing else. Yeah, it's a pleasure to be here and to participate in this series, which looks like it's really been a very interesting series. I'm sorry I haven't caught the earlier versions of this, and please put me on your list for coming up. Just as a logistical part, I really prefer it if people ask questions and put them in the Q&A while they're going on. And so if you can actually pop things into the Q&A, I'll see that the questions are there. And then at an appropriate point, I'm going to stop along the way and look for questions in the question and answer. Otherwise, it feels too much like I'm just, in my living room with all my books talking to my screen, which I guess I am. But I would much prefer.
Fortunately, you are.
Hey, got to be somewhere during the pandemic. All right, I'm going to share my screen to talk with you about quantum machine learning, and specifically quantum machine learning for financial systems. Now I'm going to first talk very generally about quantum machine learning and why it might be that it could be useful for analyzing the kinds of patterns that arise in financial systems. And I should say that we actually don't know right now if the generation of quantum computers we have can help with financial problems and financial analysis. I note that there are many seminars and conferences on the web for quantum computing about economics and finance and things like that. I want to make it clear that we don't know if it actually is going to give an advantage, but it might. And let me say why it might. So now I'm going to share my screen. Let's see if I can do this. Okay. All right. I hope you can see my beautiful PowerPoint slides here.
Yes, we can.
Good. Great. I've actually never made a PowerPoint slide in my life, and I intend to go to my grave with never having done so. So, so I'm first going to talk about, the first part is about quantum machine learning, and then I'm going to go to talk about possible applications to finance along the way. I have some more specific slides here about technical aspects of the quantum algorithms, but I believe this is quite a general seminar series, and I will only go into these technical aspects if people make me. Of course, it's very easy to make me do that because I like talking about the technical aspects. But I think, but I wanted to make sure that we get the general point across. And I already gave the most important point, which is that we don't know if quantum computers are going to help with financial problems. But now let's look at why they might be able to do so. So what are the motivations here? So what do we do? What do we know that quantum computers can do better or faster than classical computers? And by the way, they don't do it yet because the current generation of quantum computers is still insufficiently powerful to take advantage of these theoretical enhancements. However, we are in a very exciting time for quantum computing because people are trying to build quantum computers lickety-split. Google and IBM and Microsoft and Amazon and Huawei and Tencent and all those folks are vying to be the first people to corner the quantum market. And as a consequence, the technologies for quantum computing are going ahead by leaps and bounds. So the kinds of things I'm talking about here might very well be available in the next few years. Anyway, what do quantum computers do that classical computers don't? Well, quantum computers, excuse me, pardon me, they can perform linear algebra exponentially faster than classical computers. That's the basic reason. And I'll say why they can do it in just a second. It actually has to do with the fundamental nature of quantum mechanics. That the mathematical formalism of quantum mechanics says the states of quantum systems are vectors in a very high dimensional space. And when I take those vectors, the dynamics of quantum systems basically is described by multiplying those vectors by gigantic matrices. So the underlying formalism of quantum mechanics is all about linear algebra. And if you're clever about it, then you can actually convince quantum systems to do this linear algebra in ways that solves problems that we might be interested in solving, such as financial problems. So that's the first aspect of quantum computers. They're really good at linear algebra because linear algebra is what quantum mechanics is all about. Now, it's also well known, and has been known for a long time, that quantum systems can generate patterns in data that classical systems can't. Now, quantum systems are famous for generating strange and counterintuitive patterns in data, for generating what Einstein called spooky action at a distance, except he said it in German, spukhafte Fernwirkung, which sounds great. Sounds better in German, I think. They exhibit what Schrödinger called entanglement. They have patterns, they exhibit patterns. More recently, people talk about patterns such as quantum supremacy, in which quantum computers generate patterns classical computers can't. So quantum systems have been known, but they've been known for 100 years or more to generate patterns in data that classical systems can't. So this suggests using them for quantum machine learning, because in machine learning, we have systems like deep neural networks that can recognize patterns, and they can also in data, and they can also generate patterns in data. So we can use them in recognition mode, and many systems we can use in generative mode. So for instance, there's a famous Google experiment where they taught a deep neural network spontaneously to figure out that there are lots of pictures of kittens on the internet. And so it could recognize pictures of kittens, but it also can be operated in generative mode. So if I gave it a picture of Eric here and said, what do you see? It would generate a kittenish picture of Eric looking very, sweet and fluffy, and well, maybe with some sharp claws there. But so in machine learning, we have these systems that can generate patterns. Now, in quantum systems can generate patterns in data that classical systems can't. So we can reasonably hope that quantum systems may be able to identify and classify patterns in data that are classically inaccessible. That's a reasonable hope. And this turns out to be true. So let me describe how this works. So please I don't see any questions in the Q&A. That's the end of the introduction. Please pop some questions in the Q&A so that I know that there are people out there. But meanwhile, while I'm waiting for the questions to show up, I will tell you what's going on here. So let's see what's going on here. So here,
maybe I'll have a question. So you're mostly talking about deep learning, I gather, which is sort of the hidden layers of the deep learning are in a classical computer. Can reach patterns that are different, that are not as rich, I guess, is that sort of the argument, than the deep learning patterns hidden layer patterns that you could harvest from a quantum machine.
Yeah, though in fact, I'm not I'm not going to talk that much about deep learning. I'm going to talk about a variety of different methods, some of which can be performed by neural networks. When I started working on these quantum machine learning problems back in 2012, when my postdoc, Patrick Rebbentrost, came into my office and said, "Hey, Seth, we should look about quantum algorithms for machine learning." And I said, "Great, what's machine learning?" Because I didn't really, I kind of knew, but so he started telling me about support vector machines and kernel methods and clustering algorithms and embedding methods and which I'm going to tell you about how you quantize them. And then he told me he said, "Let's look at deep learning." I got all excited because I thought that, it meant that computers could learn stuff that was deep, like things about like love and truth and happiness and, the nature of the universe. And then he said, no, it's just like these deep neural networks. But it is true that deep neural networks, when you quantize them, that the quantum versions of deep neural networks can provably generate patterns that you can't generate classically. What's not known is whether quantum deep neural networks, again, can learn and classify patterns that can't be learned and classified classically. But I will give examples of cases where quantum computers can indeed do that. Oh, and I see a question in the Q&A, and this is very exciting. Oh, yes, do present NISQ devices can be useful for quantum machine learning? Yeah, so that's a very good question. And I actually, again, as I said, it's not clear. We don't know if quantum machine learning will work well on NISQ devices, on NISQ standing for, I always forget what it stands for because I hate acronyms so much, but it stands for near-term intermediate scale quantum devices, which have like 100 qubits, can do like 10,000 operations, aren't fully error corrected, or for special purpose devices that people are making now. I think that one can reasonably hope that one might be able to do this on NISQ devices. I don't think that we're going to have to wait around. My guess is we're not going to have to wait around for full fault tolerant scalable quantum computers to do quantum machine learning for reasons that I'll talk about below. And that's good because the expected time to get, large scale, fault tolerant, scalable quantum computing is something like 15 years plus or minus never. So it's, well, maybe not minus never, but plus never, right? Like -7 plus never. That's where the error bars stand, right? So it's good that we might be able to do this on the near term and on special purpose devices. And I'm going to argue that we can do that. We ought to be able to do that. So here, let's look at these linear algebraic methods. So let me just mention why it is that quantum computers do better. So I explained why quantum computers are good at linear algebra. It's because quantum computers are all about linear algebra. That is, here, if you look right here, if you can see my pointer, if I have a vector of data x, I can map it to a quantum mechanical state. This, like, for those of you who are not quantum mechanical people, when I put something in these funny brackets right here, they're called Dirac brackets. It means whatever's in there is quantum mechanical. All right. So the logo of Google, the Google Quantum Group, is Google in these Dirac brackets. So I can take a vector over n with n components and map it to a quantum state over log n quantum bits. So that's a tremendous enhancement in terms of compression, in terms of the representation of data. Just to give you an idea, I can take 300 quantum bits can store a vector, the components that has 2 to the 300 components. And I picked 2 to the 300 because 2 to the 300 happens to be the number of elementary particles in the universe. So with 300 quantum bits, I can have a vector on a vector space that's so large, I need a classical computer the size of the universe to actually register this in data. So that's potentially useful. And indeed, when you find out that for these basic linear algebra subroutines, the BLAs, this goes into MATLAB, you look at the quantum versions, you find things like the fast Fourier transform for finding periods in data. The classical version, if my vectors are n-dimensional, they go as order n log n, that's great. The quantum version goes as order log n squared. So again, it's like 2 to the 300, classical computer is never going to do that. That would take, you know, if n is 2 to the 300, it would take the age of the universe to do a Fourier transform on something that's the size of the universe. Quantum computer, that log n is 300. 300 squared is 10 to the fifth, right? So it would take 10 to the fifth steps on a quantum computer. So if you can phrase things in terms of these linear algebra subroutines, then you're in good shape. So similarly, finding eigenvectors and eigenvalues of matrices, you know, order n squared on a classical computer, or log n squared on a quantum computer, you detect a pattern here. Inverting matrices, so if I want to say, oh, I have a big matrix AX, and I want to solve the equation AX equals B, so X is equal to A inverse times B. On a classical computer, you can do this in time order n log n using conjugate gradient descent. That's already really amazing. You do order n log n. In quantum computer, it's order log n squared again. So these quantum computers in principle, and actually in practice for doing these kinds, people of course have demonstrated experimentally all these quantum basic linear algebra subroutines on small quantum computers. In practice, we're not at the case where we can actually use these for machine learning yet, but you know, this looks good. And indeed, for data access, the real bottleneck, I claim, is the problem of data access. That is, if we have a humongous vector of data stored in random access memory and RAM, the problem here is to map it into this quantum state over many, many fewer qubits. And for this, we need quantum random access memory. So the main issue main technological issue in implementing the quantum machine learning algorithms I'm described for you for financial applications or other, is in fact this data access, encoding the data in a quantum state using quantum random access memory or a variant thereof. That is the key issue, technological issue that needs to be solved. And along with, of course, building the quantum devices that Google and IBM and Amazon and all these folks are straining right now to try to build. But I actually, just looking at the progress that they're making, I think they're doing a pretty darn good job. And I expect devices that suffice for, in this era, devices that suffice for machine learning to be around soon. Okay, good. And I see more Q&A. What kind of machine learning from Hema Chilukoti? Unsupervised, supervised machine learning, unsupervised machine learning, reinforcement, quantum computing mostly useful for? The answer is all of those, and I'll talk about that in just a second. Oh, and here's one from Abhijit Rao. With a hybrid quantum classical approach, can machine learning tasks be partitioned? Is it fair to assume that some tasks you identify are more efficient on today's quantum computer and being done in practice? That's a great question. And I think that, let me answer that right away because it's such a great question. If we look at the algorithms that we've been developing for doing quantum machine learning, the ones and where we simulate them and we see how they work, the ones that work best are the ones where we combine quantum machine learning and classical machine learning in a hybrid fashion. So you do classical pre-processing of the data in order to encode it in a form that's useful for putting into a quantum computer or a special purpose quantum device. And then you process that information on the quantum device, and then you measure at the end. So we anticipate, we actually find when we simulate what's going on with these quantum algorithms that a hybrid classical quantum approach that combines, for instance, classical deep learning with a small quantum computer is what works best. Maybe not surprisingly. Go ahead.
Do you mind if I say something? So I mean, I know that you talk a lot about the linear algebra and the speeds up implied by that. There is obviously also a big chunk that doesn't require all the input-output, which is the quadratic speed up on Monte Carlo simulations.
Yes.
On quantum machines that speed up things that we cannot compute analytically, in particularly derivatives, financial derivatives, and there their probably progress is more promising, I would say,
Right.
in the short term.
I agree. I agree, Eric. That's very important. So, thank you for bringing that up, because I'm not sure I was going to mention it. It comes at the end of this talk. So, generically for quantum computers, these are exponential speedups, but also for quantum devices in general, you get a generic quadratic speedup. So something that takes time and on a classical computer, like optimization or doing Monte Carlo, that goes from, to simulate n steps of a classical Monte Carlo on a quantum computer requires square root of n steps on a quantum computer. And that's potentially very useful. Of course, then you're always there and you have a tiny quantum computer competing with a gigantic classical computer. And so it's hard to know who's going to win. And but in fact, one of the charges that the people from the finance industry who I've talked with, like bankers, for instance, say, we really want to speed up on Monte Carlo. And I'll make sure that I have enough time to talk briefly about this, but I'll say it right now in case I run out of time. So it turns out that you get it for Monte Carlo, there's a generic square root of n speed up for Monte Carlo, which is good, because the bankers say to me, they say, yeah, our main task is to figure out how much supercomputer time we need. At 5 p.m., we have to figure out how much supercomputer time we need between 5 p.m. and 9 a.m. to do the Monte Carlo we need to make the decisions we're going to make tomorrow.
Correct.
So if one could actually speed that up, that would be great. Now, recently, my group came up with an exponential speed up for the analysis of Monte Carlo. So we can show that you get a quadratic speed up for performing the Monte Carlo, but for actually analyzing the results of the Monte Carlo, you can actually have an exponential advantage over classical computers. And that's, of course, very important for the kinds of things, for people who are doing things like simulating, derivatives and options and variance.
Large portfolios. Right.
So I'll make sure I get to that. Yeah, let me move ahead then. So I'll just mention I want to make sure that we're on schedule. So let me just move to the end of the introduction here. So if you actually look at these kinds of basic linear algebra subroutines, and look at the quantum versions, and you look at kind of machine learning and data analysis that gets exponential speedups from linear algebra, you find that cluster finding, like k-means, for instance, but other kinds of cluster finding methods, these are purely linear algebraic methods. Support vector machines, where you have clusters of data embedded in a high-dimensional Hilbert space, the so-called kernel method, and your goal is to find the optimal separating hyperplane between them. These get an exponential speed up. Just simple least mean squares data fitting, right? So if I want to I have some data that lives in a high-dimensional space, and I want to fit some hypersurface that gives me the least mean squared error to fit this data. This is the original application of data fitting methods developed by people like Laplace, right, in the 1700s. This gets an exponential speed up on quantum computers. Principal component analysis, which is also kind of almost the first thing you do for data. We'll see in just a second that gets an exponential speed up, as do methods like gradient descent and Newton's method. All of these bread and butter classical data analysis methods get exponential speed ups. And actually topological analysis of data, which I note is something that people, from looking at the literature, I had a long discussion with the folks at I know it seems absurd to me now, or I wouldn't have believed this 3 years ago, that Morgan Stanley and Goldman Sachs would have had their own dedicated quantum computing groups. If you told me that 5 years ago, I would have just laughed, but it is the case. I had a very nice long talk with the folks at Goldman Sachs a month or two ago about the use of quantum algorithms for topological analysis of data to apply to financial data, where I gather that people basically, you have a time series, you embed this time series in a very high dimensional space, and then you analyze the topology of the vectors that are your time series in this high dimensional space. And then a change in the topology of the data says bad stuff is going down, or like, something's about to happen. I won't go into greater detail about that. I just want to note that we have if you want to look, we have at our papers on topological analysis of data, then they apply directly to this kind of topological analysis of financial time series, which people apparently use. All right, let me move ahead here. Let me actually give a very simple example, financial example. This was really the first financial algorithm that we really looked at. This is classical Markowitz portfolio management. And by the way, I'm aware that this is extremely simplistic and nobody does this, right? But in fact, there are many variants on this. And so I just like to show you how this kind of thing works. So I'm sure people are familiar with this, but I'll just go over it anyway. Suppose we have a set of vectors of historical returns. Let R be the returns of all the stocks on the stock market. Let J be, I don't know, either a tick by tick or day by day record of the returns. So R0 is the returns on day 0, R1 the return on day 2, etc. And the average, we have an average return over the M days or M ticks that we have. Of course, we could, weight this by having more recent data be more important than older data, et cetera. And then, but anyway, this is our vector of historical returns. And then we have a covariance matrix C, which gives us the linear correlation coefficients between these historical returns. So here I've got this covariance matrix. And for instance, the 3, 5 entry of this covariance matrix is the linear correlation coefficient between stock 3 and stock 5. Now, the kind of cool thing about this is that in the quantum case, whoops, what happened to lost my talk here. Okay, in the quantum case, then these vectors then correspond to quantum states. And again, you have an exponential compression. If I have, n these vectors, if I have n stocks, then the quantum states are over log n qubits. And then actually the covariance matrix just turns out to be what's called the density matrix for these vectors. It's just a statistical mixture of these quantum vectors. And that's extremely useful because then we can actually sample from we can use these vectors of historical returns to sample from elements of the covariance matrix. Anyway, the goal of classic Markowitz, 1940 portfolio management is you have a vector of wealth. W is the vector, and its entries tell you how much of your wealth you're going to invest in each stock. And you want to maximize your expected return for fixed risk. Or equivalently, from the mathematical standpoint, if you pick your expected return, you want to minimize your risk. And so the risk, this is the covariance matrix. This is just the standard deviation of your return, and this is your expected return. And so what you'd like to do is you want to find, actually your goal is to find the optimal risk return curve. So, if you can get higher returns for more risk, for greater risk, and at a certain point, as the risk goes up a lot, you may get high expected returns, but you probably don't want to do that. And so this is this blue shaded area is the set of obtainable predicted risk returns. And you would prefer to have this orange point that's on the optimal risk return frontier, rather than this green point, which has lower return for the same fixed risk. So the goal is to find this. And this is actually just a linear algebraic problem. You just set up the following Lagrangian. Here's the thing you're trying to maximize, the expected return. You set a Lagrange multiplier that says we want to minimize, or we want to fix the risk. And then we just take a variational approach, and we just have to solve a linear equation where we have C times W. Our W is what we want to find, and we have R, which we know, and we know C, the covariance matrix. So we would just need to invert this equation. And the quantum mechanical version is just the same. And you can just use the quantum matrix inversion to solve this exponentially faster on a quantum computer. Okay, so that's that's the kind of thing that, I mean, by now we proposed this a long time ago now, but and it's not, this is not surprising that quantum computers are good at this. A surprising thing is that excuse me, it is a spam call. A surprising, quite surprising thing that came up just in this last year, which I'd like to mention particularly to this audience, is that it turns inspired by these quantum methods that are exponentially better than the classical methods for this kind of problem. Ewan Tang and then I and Andros Gillian and some other folks realized that you could actually make classical algorithms that are inspired by these kinds of quantum methods that might in fact allow you to analyze data classically and get this same kind of information classically, so-called quantum-inspired algorithms, if you look them up. And together with the folks at Xanadu, the quantum computing company, we actually simulated what happened if you run these quantum-inspired algorithms on actual return data for the stock exchange. And we found actually it worked. And I'm not sure that we have not yet, I'm not sure, again, this is a very simplistic picture right here, but there are classical, quantum-inspired classical algorithms that might also work for this. Okay, keep those questions coming. I don't see any new ones, so just like when I see the number, the Q&A go from 3 to 4, I'm going to answer your question. Aha, look at that, great, that's what we want to see. Okay, this portfolio optimization is limited to equality constraints. Are there existing methods using inequality? This is an awesome question. And the answer is, I wish. I wish there were. Thank you, Eric. In fact, for folks who are familiar with optimization using inequality constraints, it's a harder problem than the equality constraints. For example, the inequality version of this Lagrangian method is, I would say, oh, I want to say this risk is less than or equal to a certain amount. And if the solution lies in the interior of the space here, this can be a very hard problem to solve. I mean, here you would get a Lagrangian problem with so-called Karushkin-Tucker methods, and you have to solve the Lagrange equation, and you find feasible points that might be the solution, and then you have to evaluate to see if they are solutions, and we don't know how to do that on a quantum computer. And there are dynamic programming methods for quantum computers, but they don't give exponential speedups in general over classical computation. So if somebody out there in this audience or anywhere else could come up with a method for doing optimization with inequality constraints on a quantum computer, my hat would go off for you, and I think the world would beat a path to your door. So great question. So let's now turn to this question of generating data, and let's look at this problem of generative adversarial networks, or GANs. And we're going to look at the issue about quantum GANs, quantum generative adversarial networks. So I'm sure that folks there know about generative adversarial networks. It's a very sweet way of training a generator to generate fake data that mimics the statistics of real data, which of course is very useful in financial markets, right? If you want to be able to, you'd really love to be able to, I mean, let's just be realistic, right? You get a bunch of real data from the historic stock returns, for instance, and if you can make a generator that generates data that has the same statistics, then you can statistically predict what the markets are going to do. And if you're right, then in principle, you'll make a lot of money. In practice, of course, you can just lose your shirt. But of course, that's the way things are, right? So, so let's look at this. So now this is something the Christian Wiedbrook, the head of Xanadu, and I wrote the first paper on this back in 2018. Now there are dozens of papers on quantum generative adversarial networks now. The idea is simple. So we have a discriminator, whom I'm going to call Alice, and she has to discriminate between either real data or fake data. And Bob here is going to be generating the fake data here. And it's the generative adversarial network is, and I've described this in quantum mechanical terms, rho is just a quantum state, sigma is a quantum state. And so Alice wants to make a quantum measurement that's going to distinguish between these two. And the way it works is Alice is presented with either a piece of real data or a piece of fake data. And then she's going to make a measurement that's going to minimize her probability of error. She wants to maximize her probability of successfully distinguishing between the real data and the fake data. And she has an adaptive method, such as a deep neural network, that allows her to make this measurement. So first, we fix the statistics of the real data and the fake data, and then she adapts her measurement to distinguish optimally between them. And then Alice fixes her measurement, and then it's Bob's turn to try to fool her by generating fake data that will fool the measurement that was really good at distinguishing between the real and fake data before. And so now he gets better and better at generating the fake data. So you see it's an adversarial game where I'm just phrased this in quantum mechanical terms. In quantum mechanical terms, everything is matrices, so the measurement corresponds to a matrix. And Alice is trying to maximize the expectation value of this will just be the probability of her distinguishing correctly between the real and fake data. So she's looking on this set of positive matrices, and Bob is just trying to minimize the norm actually between the real data and the fake data. And it's a game, an adversarial game, and actually you can show that you can apply game theory and Nash equilibrium theory, and you can show that it actually has a unique Nash equilibrium in which the fake data actually over time, as you play this game many times, the fake data gets closer and closer and closer to the real data. So this is very nice, and we have nice actually experimental demonstrations of this. It's actually rich, just in the case of ordinary generative adversarial networks. Even though you do have a unique Nash equilibrium, you may also find that there are instabilities in which the generator and the discriminator chase each other around the strategy space, which is and never actually arrive at the Nash equilibrium. So interesting and entertaining things happen. But quantum mechanically, this is great. Moreover, quantum mechanically, here's a case where we can actually prove that if the actual real data is being generated by a quantum mechanical system, then a classical system can't generate that same data. This is the phenomenon that I was alluding to before, as in, for example, quantum supremacy or these weird, funky, spooky action at a distance. This data these statistics can't be generated classically. So you can't actually reproduce that quantum data classically. So here's a case where at least we can prove for a specific case, that is the real data is being generated quantum mechanically, that you can't reproduce it classically, but you can reproduce it quantum mechanically. And I have, and I will skip over, this is a technical version of this. We have a recent paper on this for those who like quantum generative adversarial networks. We have a version based on the quantum version of Earth movers distance, or Wasserstein 1 distance. So the classical version of this was actually invented by Gaspard Monge in 1781. He was a buddy of Laplace's, and it's a metric between probability distributions. But I don't have time to go into the details of this, so I won't. Let me go ahead. So now let's look at deep quantum learning. This was Eric raised this question before. Let's look at the quantum version of deep neural networks are simply quantum circuits where the individual quantum logic gates have tunable parameters in them. And so this is like a classical neural network where the weights, in classical neural network, you typically have a fixed nonlinearity preceded by a linear transformation, and the weights of your deep neural network are the variables in this linear transformation. So in the quantum approach to deep quantum learning, the way that people talk about it is we have a network, and we have quantum logic gates that operate on our quantum variables. And then each possible quantum logic gate is parameterized by a bunch of different possible parameters, and these parameters are now the weights. So I get a transformation of my initial state. This is this u of theta, which is a function of these weights. And the goal is to adjust these thetas, the weights, to optimize the overall transformation, just as in a classical neural network, except now everything is quantum mechanical. And people build lots of systems to do this. They don't have to be, it doesn't have to be a fault-tolerant quantum computer, but you can make special purpose superconducting circuits for this. You can implement systems like this on ion traps. You can use linear and nonlinear optics. All of these have been experimentally demonstrated. Moreover, in fact, in all of these methods, there are quantum startups popping up like little quantum mushrooms out of the ground these days to try to actually do this kind of stuff. And let me give you an example of something where actually, again, we can prove that the quantum computers can do things that are different from what classical computers do. And these are these embedding and kernel kinds of methods. So the idea here is we have classical data, like say pictures of ants, pictures of bees, and pictures of cockroaches. Why not? And the goal is the embedding means we take these actual pictures and we have an embedding map that maps them into a very high dimensional vector space. And this vector space is a so-called Hilbert space. It has a metric on it. And that's what this kernel refers to. The kernel just gives us a metric on this high dimensional vector space. And then what the goal of the embedding is to embed these different, find an embedding that embeds, pictures of ants get embedded in one corner of the Hilbert space, pictures of bees get embedded in another corner of the Hilbert space, and pictures of cockroaches get embedded in another corner of the Hilbert space, so that these clusters are well separated from each other. And then you can make a measurement that will distinguish between them.
Can I ask a quick question? If
Absolutely.
So we're talking about exponential speedups. You started out talking about that, and you started out talking about that in the context of getting classical data into a qubit representation with the log rule on the transformation. That's one thing, but here we're also talking about the parameter space, which is high dimensional. So we're basically talking both about two things. We're talking about the speed up in terms of the dimensionality of the data versus dimensionality of the parameter space. Those are kind of two different animals.
Absolutely, that's a very excellent point. Right. So let me, if in this picture right here, given the kinds of quantum systems that we have these days, we don't have very many parameters to vary. So because
yeah, exactly.
The aim is in this, now we have quantum computers that have like between
not many hidden layers, not much.
Not many hidden layers, exactly. So this is in fact that's a very good point, and thank you for raising it, Eric. So this is not a case where the number of parameters that we can vary, the weight space is large. It's in fact just almost the opposite case that you have classically. Classically, you've got these humongous weight spaces with 10 to the 11th parameters, and there are many more parameters than there are data points. So this is in fact a case where when we actually simulate these methods, these embedding methods, what we do is, in fact, we have classical pre-processing of the data. So I would have it over here in this empty space right here. I have a deep neural network that's going to take our data, and then the output of the deep neural network is going to be the parameters that we're going to use for our quantum network. That is, so we're going to, the deep neural network is going to compress the data into a quantum state, and then we're going to actually use these parameters to try to embed the data in a good way. And we co-train the hybrid classical quantum system to actually perform this embedding. And that's really necessary for exactly the reason that you mentioned, that we just don't have quantum systems where we have a gajillion parameters in our deep, they're not deep quantum networks, they're shallow.
Right.
However, even for shallow quantum circuits, you can prove that the set of embeddings that you obtain are not obtainable classically. Just in the same way for the quantum GANs, the quantum generative adversarial networks, you can't get the kind of statistics out of a classical system that you can generate out of a quantum system. For embeddings in a Hilbert space, the embedding in the Hilbert space or the vector space of quantum mechanical states, the statistics of the measurements you get from that cannot be obtained by any kind of classical system. So at least we have a proof that the embeddings for these kernel methods that we obtain are not obtainable classically. And that's, of course, this is a classification method. Again, for financial systems, this would be something where it would be, I think you would probably want to apply it to situations like I was mentioning about the topological data analysis, where it's like, okay, this is kind of like some kind of normal situation. We want to say, is the new situation a normal situation, or is it some kind of abnormal situation? So let me actually finish up here, because okay, this is more on this variation of quantum embedding. Let me finish up with the promised exponential advantage of computers for doing Monte Carlo. Because this is a neat result, and we were very happy with it. And this is a generic problem in quantum computers. This is the archive number for this paper, if you want to look at it. There's great progress in making quantum hardware, but we actually don't have great applications for this. And as I mentioned, I've been casting around for years now after getting, when bankers come and say, we need better quantum algorithms for Monte Carlo, and we need better quantum algorithms for Monte Carlo. And, we've got these existing quantum algorithms, which give us this generic square root of n speed up, which is great. But it's not clear that that's, given the competition between small quantum computers and big classical computers, it's not clear that that's worth doing. Can we actually get some method that gives a kind of exponential advantage? And the answer is yes. And I'm going to show how we get, when we have this exponential advantage for solving different, for inverting matrices, I'm going to actually show that we can actually get an exponential advantage for analyzing the data in Monte Carlo. And I'm out of time here, so I'm just going to say this very briefly. So let's look at continuous time Markov processes. Actually, the ones we analyze in the paper are, while we were writing it during the pandemic. And so we started off with epidemiology. That was our first continuous time Markov process. And then we said, we need another example. And so it was before the election. So we decided to look at the spread of political opinion on complex social networks. We managed to get it posted before the election. And so I'm not saying we had any influence on the outcome of the election. And I'm also not claiming we've had any influence on the spread of the pandemic or keeping it spreading. But our next paper on this is actually going to be exactly on analysis of black shoals, data. So in case there's an upcoming financial crisis, we want to be topical about this. So again, we have classical Monte Carlo, efficient estimation of expectation values for stochastic processes. And we get a square root of n speed up generically from this nice work of Ashley Montanaro in 2015. I will just say what happens. So what we find out is if we do the classical Monte Carlo, the quantum version of this Monte Carlo operates by mapping the vector of probabilities to quantum states. And then you construct a quantum state, which gives you the history of the vector of probabilities for your system. And in classical Monte Carlo, you just sample from this history. And in quantum mechanically, you get a quantum superposition of all these histories. I'm sorry, time is going up here. This is what in quantum gravity time goes up. And I'll just simply mention that if you look at these methods that I described before, way back at the beginning, excuse me, these kinds of basic linear algebra subroutines, and all of these kinds of methods that you can apply that give you this exponential advantages that you can actually, let me go back to this last slide right here, sorry. You simply find that for things like singular value transformations or principal component analysis, doing Fourier transforms to try to find the power spectrum of this Monte Carlo, or to do multi-scale analysis via wavelet transforms. These are all things that you actually can't do with just Monte Carlo sampling. It turns out that you can't do singular value transformations or principal component analysis. You can't do Fourier transforms, or if you have like gigantic high dimensional spaces, you can't do wavelet transforms because the Monte Carlo just doesn't give you the data in the right form. It's fantastic for estimating expectation values of observables, as we know. But if you do the quantum version of this to get this square root of n speed up, and you get your answer as a quantum state, I'll just simply note in the paper that I described there, now do this data analysis using these kind of quantum data analysis methods that I mentioned before, like these ones right here, you find that the analysis of the outcome of your quantum Monte Carlo simulation is exponentially faster than the classical analysis of the same things. So if you're actually analyzing, if you look at the analysis of the outcomes of Monte Carlo for this kind of thing, bread and butter, principal component analysis, singular value transforms, power spectra, et cetera, that the quantum algorithms for analyzing the quantum state, that solution of the Monte Carlo, is exponentially faster. So that's great. And
this might be quite interesting if once you start thinking about Markov chain Monte Carlo, where you're, as you said, you're not necessarily limited to thinking about expectations, but you actually want to have a quantum representation of the entire Monte Carlo simulation. outcomes, and then sort of characterize that and look at it actually in a very intelligent way. I really like this actually.
Well, in fact, you just summarized exactly what's going on here very well, better than I did myself. I'm probably too immersed in it. Yeah. So the quantum algorithm works because you just get the whole history of the classical Monte Carlo,
right,
the entire history of the probability distribution, and then instead of just getting samples from it. And if you have this entire history in quantum superposition, then you can do all this fancy pants quantum analysis of it, and it gives you information that you couldn't have classically. So,
very smart.
and I'm anybody who has suggestions about this, we're, as I say, we're kind of single-mindedly moving to apply this to black holes as our next example, because it seems like the obvious simplified example to look at, because people burn a lot of classical Monte Carlo and black holes, as my understanding. So anyway, if anybody has other applications, it's, our minds are very, very open because we're very, very ignorant. So we have nothing but open space in our minds. Okay. So there's another question in the Q&A, and I'm almost done. Okay. Right. What advantages, opportunities, if any, do you see in usage of open quantum system for Monte Carlo simulations? That is a fantastic question. That's from Travis Hurant. Fantastic question, Travis. I don't know the answer to that one. Everybody keeps asking these great questions to which I don't know the answer. So this is, of course, this is a coherent. We create a coherent quantum simulation of what's going on. But of course, if I have an open quantum system, I'm going to get, an incoherent probabilistic dynamics for the system. And instead of having a pure quantum state to do this analysis, I'm going to have a mixed quantum state. And I don't know, and I don't think people in my group know either, what the answer is for to the extent to which we can actually apply these methods or potentially other methods to open quantum systems. So I would definitely like to know the answer. So if you figure it out, let me know. Okay, let me just stop by ending that actually, so remember this question I say is a big bottleneck. How hard is it to put question? How much information can you pop into one of these shallow quantum circuits that we have during the decoherence time? This was the question that Eric was asking before. I mean, you guys ask great questions, I got to say. I don't know the answer to all of them, right? The question of like how many parameters, if we have these thetas, and these thetas are being determined by zapping our system with lasers or microwaves, just how many bits can we cram into a quantum system during the coherence time? Well, the answer, of course, is not as many as into a classical computer for sure. But I'd like to argue that in fact it's not that bad. So I'm going to end up with that because we're out of time, basically. So basically, if you look at just like you do Shannon theory, like about, I say, what's the bandwidth of my lasers or microwaves? How many bits per sample do I have? How many bits I have? You just say the answer is, the number of qubits times the bandwidth times the bits per sample is the total times the time is the total number of bits you pop into the system. It's a very simple formula. Thank you, Claude Shannon. And so you just do this analysis for, say, superconducting circuits. These are the circuits we have now, right? And it's going to get better in the future. You find that you can get around 10 to the 10th bits loaded into quantum states in superconducting circuits. This is just actually so this is a 33 qubit superconducting circuit or something like that, right? Well, if you could have 100 qubits, that'd be fine. For atoms or ions, you can get a lot more. I mean, you can get 10 to the 12th bits, even more. You can get, terabyte into these systems right now. So that's a fair amount of information. And together with classical pre-processing of the data to make these hybrid systems where, you pre-process the data classically, you pop it into your quantum system. Now you do quantum processing of the data. So the quantum processing takes place on numbers like this. The classical pre-processing, reduces the large size of the classical data space into something that's palatable for a quantum computer. So I'd say that's doable. And with that, I'm going to say thank you for your attention. And thank you for all your excellent questions. And I'm happy to answer more.
I think there's more in the chat, in the Q&A.
Oh, here's one in.
There are two more actually.
Two more, excellent. Okay, great.
Go ahead.
All right, one from Dylan Herman. By the way, I'm really anticipating this because I'm sure I'm not going to be able to answer it. Right. When forming the Lagrangian for the portfolio optimization problem and formulating as a quantum linear systems problem, AX equals B, B is typically very sparse. It was mentioned in a paper by Scott Aronson that the speedup in this case is expected only to be quadratic to go over minimum search bound. Oh, you mean if it's not sparse, right? So do we only expect a quadratic speedup for portfolio optimization then? We would like your thoughts on this. Thanks. Okay, yeah. That's an extremely good question. So the point here is that if the covariance matrix is, this is an older paper, Scott. So if the covariance, here A in AX equals B is the covariance matrix for the data. This is not sparse in general. So that critique from Scott, which he made basically, Scott and I, like, he chases me around and I write, my group says, hey, we can make these great quantum machine learning algorithms. And then Scott says, oh, but you got to read the fine print. I think his article is called Read the Fine Print.
Yeah, it is. Yeah.
Right. Yeah. So he said, yes, but it's got to be sparse. And then we found that we could actually do it if it's low rank, if the covariance rate is non-sparse but low rank.
It's a factor, what people call a factor model in finance, basically.
Right, exactly. Now I should say that if it's low rank, then we can also do these quantum inspired models as well, though they're much less efficient than the classical models. Moreover, in our actual analysis of financial data, this notion that the actual financial data from the markets followed, we analyze a gigantic financial data set of stock prices, and we found that it's marginal. The statement that the covariance matrix is low rank is definitely a marginal statement, which is kind of what you'd expect in an efficient market, right? If it were really low rank, then people would have figured this out, and they would be, it's the ordinary argument. If it really had all these patterns in it, then people would have figured this out and made this happen.
This can be a long conversation, but there's something called the factor zoo in finance, which is people have come up with 400 plus factors for that.
And right, in that case, it would be fine, right? If you're going to apply these like data analysis or inversion methods to things like 400 factors or more than that, so it's like if the rank effect, that means if the effective rank is just 400, fine. We're cool with that.
We have one more question.
Yeah, let's right. Okay, right. So the last question is, okay, there are two more. Xiaohan Hu. Do you see potential?
Oh, yes.
There are two more, right? Yeah. Do you see potential advantage of quantum Monte Carlo for financial problems with highly complex underlying stochastic formulations? Yeah, for sure. I mean, we're applying it to Black-Scholes because we're applying it to something that's simple and we want to do a demo. But my understanding from talking with people who really do this for something like, for instance, option pricing and stuff like that, and we have quantum models for generic option pricing also, is that people put in a heck of a lot of bells and whistles into these models just to make them more realistic, because you want to have it be as realistic as possible without overfitting the data, which is a tricky thing. But these quantum algorithms should be fine. You want to have a really complex model, that's fine. That's the whole point, is that the quantum models can operate on very high dimensional spaces, and with all kinds of different features in them. So for each one, you kind of have to analyze to see how it works. But yes, that's the whole point of doing this. So thank you, Xiaohan. And Peter Bordo says, what is your opinion about using Krauss operators for implementation of quantum HMM? What is HMM? Does anybody know? I don't know what HMM is.
I don't know what HMM is. That's
hidden Markov models. Hidden Markov models.
Yeah, that's right.
So somebody, yes, the answer. Somebody just yelled out the answer here in my house. It's like HMM, hidden Markov models. You dummy.
Yes.
All right. Yeah, good question. So using Krauss operators for implementation of quantum hidden Markov models. They're actually open quantum systems. Yeah, so this is a really interesting question. And again, I talked about this a little about the open quantum systems. This exponential advantage for analyzing, Markov models, hidden or otherwise. I know we have it for the coherent case, but for the case when you have like a stochastic open quantum system, I don't know the answer. So I'll say that before. I said that before, but since it's a very open question, I will say something more about it. So it is known that if you look at the quantum version of hidden Markov models, which are kind of they go into things like quantum epsilon machines, where I have internal quantum states. I have Krauss operators. For folks who don't know what Krauss operators are, they're just the mathematical mechanism for updating these quantum hidden Markov models. It is known that you can reproduce even just classical data sets with more compact quantum hidden Markov models than you have classically. So you can have, there are examples where the classical hidden Markov model has you require 4 states and the quantum one has 2. And it would be what's not known. It would be awesome, of course. And you see how I'm phrasing the question this way. It would be great if there are cases where the smallest classical hidden Markov model for what the data has, 10 to the 12th states, and the quantum one has 42, right? Or that the classical one has 10 to the 12th states, but the quantum one can be implemented on 42 qubits. In which case, the quantum one could have a large number of internal states, 2 to the 42 different states, which is 2 to the 42 is around 10 to the 12th, right? And it has 2 to the 42 in internal states, but you can implement the quantum one much more efficiently than you can classically. That would be awesome. And if you find out that it's true, please let me know. Yeah.
On that note, since we're running out of time, we could continue this for a long time, but unfortunately, we are running out of time.
Yeah.
I said at the beginning that this was a real treat to have you as the last speaker of the first year of our webinar series. We are taking a break over the summer and we will resume. Stay tuned. All the information will be on our website. And really, thank you, Seth. It was great to have you, and we'll stay in touch.
Thank you, and may I compliment the audience for awesome questions. I mean, you note that I was unable to answer any of them, and that's great. So
that's why you have to come back.
Yeah, if you have more, and if your questions weren't answered, just pop me an email, and I'll try to answer it.
Sure.
So I'd love to continue the conversation.